for the lab, we did number 1 for our predictions. We said that the ball is not moving at first, and it starts off staying still, and then it pushes back down it with the force. And then for our observations, at first it was not in motion, then we pushed lightly, harder, then even harder to speed it up. As a result, the bowling ball rolled faster and a greater distance. And for the worksheet 1A, we had number 2 and number 3. Right here we had F normal skater by ice cream. Right here we had friction on skater by skater. Friction on skater on skater.
A little louder.
Kevin, I can't read your handwriting.
All right. It happens. So, moving on to the next one, I'll help you out there. So, what was number 3? What did you have to do with number 3? Yeah.
It was the softball player who was slowing and she slides into the base.
Okay. So, in that one, they have written for the bottom one, they have the force going up. It's normal on player from ground. Bottom is gravity on player by earth. And then they have 2 forces going left and right. You have force, looks like friction on player by ground, and then the other one is force of friction on player by ground. So basically they have 4 forces, 1 up, 1 down, 1 left, 1 right. The up and down ones are equal, the left and right ones are equal, at least in the second one. For question number 2, they have 4 forces again. 1 up, 1 down that are equal, 1 left, 1 right that are equal. Okay? So let's go ahead and let's look at this. All right, do we agree? Do we disagree or not? What? What do we think, guys? Let's take number 2 first. Do we think there should be 4 forces? Do we think that they're right? What? Don't look at me, you look at them. What do you think? You only have 2 forces. Speak up, man. Why? Okay, what forces don't you have that they have on number 2? Huh? Fn and Fw. Well, that should be F and G. So you have normal force and weight. Okay? Are there any forces going left and right on that thing? On that girl? No. She's sliding. So there should be no left and right force. Very good. All right. Kevin, it stays on the board. All right. Number 3. What about that one? We've got 2 forces, 1 up, 1 down, and then 1 right, 1 left. What do we think? Agree? Disagree? What? You only have 2. You have 3. What's your 3? Okay. So obviously, can we assume that normal force and gravity in this case are equal? Yeah, because we know they're standing on the ground at least. Well, what's your 3rd force? What do you have?
Friction.
Which way? Left or right?
Left.
Left. Why don't we have a force going forward? She's sliding. For anyone that's played baseball, who's a baseball player? Isn't there someone here, a baseball player? Oh, there we go. I knew we had one. Okay. Question. When's the last time when you were sliding that you were running at the same time? Doesn't happen, does it? So is there any forward force? So what should be the only force? Backwards. Okay. Very good, gentlemen. Thank you very much. All right. Kevin, close it. Stop it. Shh. Go ahead. Ladies, are you recording? Kevin?
Yeah, recording.
Go.
For number 4, we got that there was force of gravity on the lamp by Earth, and force of tension on the lamp by the chain, and a force net of degree of 0. For number 5, the force of tension on the bucket by the rope, and the force of gravity on the bucket by Earth with a force net of 0.
For number 1, it was a bowling ball from Raspberry Prediction where he pushed the right.
Our observations were that we push the ball continuously at a constant speed.
Let's take a look at 4 and 5 first. So, number 4, what do we think? Do we agree with them? There's only 2 forces on it, up and down?
Yes.
Cody, what do you think? Number 4. You agree with what they wrote? Or? Okay, why? Why is it FT? What does T stand for, Cody? Okay, so why is that tension in that question? Why would that be tension, not normal force?
It's keeping it up.
What's keeping it up? Okay, very good. It's a chain. It's something else holding it up instead of it pushing off it. Very good. All right, so let's go to number 5. Now, number 5 has the 2 forces equal. Wait a minute. It's moving, though. Why are the 2 forces equal if it's moving? How can they be equal if it's moving? Well, what?
I don't think they should.
You don't think they should be equal. Why?
Because it's moving up.
Okay, it's moving up. What?
Nothing.
No, you were saying something. We'll say it. What do you say?
Well, since gravity's moving.
Talk, or I'll make him point the camera at you.
Ooh, selfie.
Kevin.
Forward. Well, I was just saying, like, gravity's down. That's it.
Okay, so gravity's down, tension's up, but why are they equal? Why are they
Balance
equal?
out.
Huh?
They balance out.
How do you know?
Because when 2 opposite forces, it's stopped, right? It's neutral.
But then it wouldn't be moving. It's moving.
Force that's pulling the bucket up isn't the same as the force that's keeping the bucket tight to the rope.
Okay, so they shouldn't be the same? How do you know?
Because the bucket isn't moving
Yeah,
from
it
the
is.
rope. Well, not from the rope, but it's,
It's moving from the rope's pulling on it. Read the question. Someone read the question out loud for us, folks. Ashley, you read the question for us, please, real quick, out loud. Oh, wait, we got it over here. Say it again.
Draw a force diagram for a chandelier that is suspended.
That's the wrong one. We're looking at number 5. That's okay.
Oh, I was looking at the picture on it.
It's okay.
Draw a force diagram for the bucket of water that is being raised from the well at a constant speed. Label the forces and use the quality marks on the force diagram.
What do we know about its velocity?
It's constant. It's constant speed.
What happens if there's a force, an unbalanced force applied to something? Cody, what happens when there's an unbalanced force applied to something? When there's a force in one direction that's bigger? You go in that direction, but not just that. What happens to your velocity? It increases, doesn't it? Because, or decreases. You accelerate. What's the bucket doing? At,
A constant speed.
so therefore, what do the forces have to be? Equal. Don't doubt yourself. I just had to make them prove it. They're equal. Because it's going at a constant speed. Stop doubting yourself. Thank you, Kevin. All right, he's going to take over. All right, go ahead, gentlemen.
number 6, we got skydiver falling from a plane. Force pulling down gravity on a skydiver by the Earth. And force that's pushing against them is lift on skydiver by air. Number 7, we got skydiver who is ascending at a constant velocity. Force pulling down is gravity on the skydiver by the Earth, and force that's force pushing against him is lift shoots by the air.
I'm going to correct your guys' use of lift. Because I know in the reading it didn't really have it clearly. Lift is when something is generated based on the motion of the object. That wouldn't actually be lift in this situation. That would just be air resistance or resistance of motion through a fluid. So that would actually be drag. Okay? So, I mean, you're right. I mean, you're thinking lift because it's going up and down, but in reality, those would be drag. Okay? So it's okay, but you just haven't learned yet. All right. So what do we think, guys? Are they equal? I don't see any equality marks. So they're not equal, right? So which one's bigger?
Gravity in both cases.
Okay, so how would we denote that? What do we say about the arrows?
We make gravity arrow a little bit longer.
Okay, so the which arrow should be longer?
Long arrow.
Okay, so let's fix it. Just erase. Erase the shorter one. Alright, so there we go. Alright, we're going to pick it up a little bit. We're going to go a little bit faster here, guys, because we're going to record the rest of this, and we're going to close down the questions a little bit just to get this going. Alright, but the question I have for you right now is on number 7. That's the one where the skydivers has a parachute, right?
Yeah.
What's his speed?
Constant.
Constant. So what should they be?
Equal.
It should be equal because it's going at the same speed. Okay? Whenever you have something constant, all the forces are going to equal out. And that comes back to this, net force. Net force is all that forces added together, guys. So if I add all the forces together and one is bigger, I have a net force in that direction. The only time that I will have acceleration is when there is a net force. If there is no net force, there is no acceleration, which means all the forces have to be equal. Not just be equal, but they have to cancel out. Okay? All right. Thank you very much. Move on to number. Guys, I'm going to warn you.
For the homework, we got number 8, and it deals with a ball that's falling, and the only force that it's rolling. And the only force that we have is the ball is F on the ball by Earth, which is it acting on gravity, and for the bowling ball lab, we did 3, which we have to keep the ball at a constant speed on the initial velocity. And yeah.
According to your volleyball lab, what should it be doing? You had it moving at a constant speed. According to your force diagram. Looks to me like you have one really big force going in one direction, so what should that ball be doing in that direction? Well, not it, you tell me. Increasing in speed. So what would you need in the opposite direction?
Another force.
Another force. What was that force that we knew of? Why do we have to keep pushing it a little, at least a little bit to keep moving at the same speed? What were we fighting? Friction. Friction. We're fighting friction. Remember? Rough ground, bowling ball. Not exactly frictional surfaces. Very good. All right. Thank you very much. Shouldn't have earphones in during presentation. Go ahead, ladies.
So we had number 9, and the diagram was the ball going up and then it falling back down. So okay, so it had there was gravity on the ball by Earth, and then drag on ball by air is what we got. Okay. And for number 2, the lab, we had stop a moving bowling ball, and we had gravity on ball by air, normal on ball by ground, and then traction. It says traction. It says friction. Friction on ball by.
All right. So 2, not bad. You're stopping it. Very good. However, 9, not so good. Okay, Chandler, catch. Ready? Okay. Aim. Right there.
Oh.
Okay. This is last one. Question. Once the ball left my hand, what forces were acting on it?
Drag.
Gravity. Okay, drag. We're talking about drag. I want you guys to take your hand right now and move your hand through the air. Is there a lot of resistance, or do you just kind of feel the air moving around your hand? You just kind of feel it moving, right? There's no resistance. At the speed that the ball's flying in this case, is there really a resistance? No. There's not going to be any drag. However, if I threw this ball like a professional baseball pitcher, 95 miles an hour, 98 miles an hour, do you think there'll be drag? Probably. Case in point, stick your head out when you're going down the highway at 65 miles an hour. Yank! Okay? You get drag. Faster you go, more drag. It's because air is a fluid, just like water. The only difference is water is a lot more dense. Okay? So when air gets out of the way, it can get out of the way really easily. When water gets out of the way, it doesn't move as easily, which is why you can slowly wade through the water pretty easily. But if you were to belly flop off the high dive, that water ain't gonna move very far, very fast. Okay? It ain't gonna hurt. It's like hitting cement. So, in number 9, what would be the only force we should see? Gravity. All right. Thank you very much.
So, draw a force diagram for a cork floating in a water. Label the forces and use equality marks on the force vector. So, cork floating in the water, and then there's gravity acting on the cork from the earth, and that's pulling it down. And then there's buoyant on the cork from the water, and that's causing it to stay up. So they're equal, so that's why it's just sitting. And then number 3 on the bowling ball. Keep the ball moving at a constant velocity. Prediction, push it with a constant amount of force. Move. And then we pushed it and it stayed that constant. It looked like it stayed the constant force. And then the force diagram, and then there's normal on the ball from the ground, and then gravity on the ball from the earth. And then there's friction acting on it going that way. And then there's traction that's causing it.
The only reason why they were able to push with a constant force and get a constant velocity was because what did they have pushing against them? Well, what? No, I'm talking about, sorry, the lap. They had a friction pushing against them, right? So they were able to kind of push it. I'm willing to bet it wasn't truly a constant force. There were still times in which they actually were pushing it. So, but number 10, why are they equal? Why are they able to be equal, guys? Because it's stopped moving and it's not changing. All right? Okay, go ahead and thank you very much.